Section 4.1, AP Calculus, page 6. Alright, let's find the derivative at each critical number and determine the local extreme values of this piecewise defined function. Use a graph to help determine the information. So, the first thing that we're going to have to do is to find those critical numbers. So, we need to find the derivative. When we have a piecewise defined function, we can find the derivative of each individual piece, and the derivative of this top piece is -1. It is valid for when x is less than 0, and the derivative of this second piece is 2 minus 2x. It is valid when x is greater than 0. Now notice I dropped a little equal sign piece here. When you do a derivative, you don't know that the derivative is exactly, try this one more time, actually existent at x equals 0. They could be different, they could be the same. So we don't know. So just drop the equal sign there for a minute because we don't know if the derivative is defined at x equals 0. So once we have this, then let's set up y prime equals 0. Y prime is undefined, or y prime does not exist. All right, for y prime to equal 0, that means that this piece should equal 0. Could this piece ever equal 0? No. Could this piece ever equal 0? Yes. If x is 1, then that piece could equal 0. Is y prime ever undefined? And undefined is coming from a denominator equal to 0. We have no denominators up here, so this is no. Oops, none. All right, now, we haven't seen this yet. It's finally coming up. Y prime does not exist. That's when we're looking for y prime from the left side of the split. So in this case of 0, does that equal y prime from the right side of 0? And y prime from the left side of 0, that's this piece, that's -1. Y prime from the right side of 0, right side of 0 is this one. We put in a 0, and that's going to be 2. These do not equal each other, which means that y prime does not exist at x equals 0. There's a corner going on. There's a corner here. All right. So our critical numbers are x equals 1 and x equals 0. If these two numbers came out to be exactly the same thing, then the derivative does exist at that point, and the function, the derivative does exist, and then that number is not a critical number. If that happens, then you could go back and put the little equal sign back in on this one. All right, now let's keep going. Find the derivative at each critical number. So we've got our critical numbers. Determine the local extreme values of that function. So once we have our criticals, then we're going to go set up our t-chart. Actually, it's a little bit bigger t-chart here. We have x, y, and y prime. Our critical numbers, 0 and 1. All right, the y value. The y value at 0, 0 gets plugged into this piece, and that's going to give us a 3. A 1 gets plugged into this piece as well, and that's 3 plus 2 is 5, minus 1, 4. All right, now y prime at 0. Y prime at 0, that came from here. That was where y prime does not exist. And y prime at 1 is 0. All right, so what should we see in the graph? We should see a horizontal tangent at the point 1, 4, and we should see a corner at 0, 3. And right now we can't tell if those are maxes or relative max, relative mins. We can't do it completely analytically just yet. Could you see this a couple minutes ago, or was I off the screen? I'm sorry. Right now we can't tell if those are relative extreme values or absolutes. We have to graph. Later on you will be able to tell completely without a calculator if something is a maximum or a minimum. Let's sketch this graph. All right, so, 3 minus x, when x is less than 0. So y-intercept is 3, slope -1, and I have to go to the left because this graph is defined when x is less than 0. My ruler disappeared. Oh, here it is. There's that. Okay, now to graph this, 3 plus 2x minus an x squared. Oh gosh. Oh, I know. Let's come over here. I'm going to rewrite it. Y equals -x squared plus 2x plus a 3. Do you remember how to find the x coordinate of the vertex? The x coordinate is -b over 2a. So in this case, that would be -2 over 2 times the -1, which is 1. Your vertex is at 1 something. I can plug in a 1. That's -1 plus 2 is 1 plus 3, 4. We have a vertex at 1, 4. 1, 4. Leading coefficient is negative, so we know that it opens down. Coefficient's 1 out here, so same size, so over 1, down 1. Over 1, down 1, and then 3 here. And there's our graph. Are we seeing what we thought we were going to see? Do we have a corner at the point 0, 3? We do. Do we have a horizontal tangent at the point 1, 4? We do. Awesome. All right, last bit. Identify the extreme values. We have a relative minimum equal to 3 at x equals 0. And there is a relative max equal to 4 at x equals 1. And that finishes up section 4.1.